Imagine you're just, working on your computer. You are deep in the zone, trying to export this crucial document you've spent absolute hours on.
Oh, yeah, we've all been there.
Right. The deadline is looming, your coffee is completely cold, and then suddenly the application just freezes. The screen flashes.
And then you get the dreaded pop-up.
Exactly. A tiny gray box pops up dead in the middle of your monitor, and all it says, literally the only text on it, is error. Just that one word.
No context whatsoever.
None. Just error. And there's an OK button sitting there at the bottom, which honestly feels like a cruel joke. Like, it is definitely not okay. You don't know what went wrong, you don't know how to fix it, and you are just left staring at this vague, entirely unhelpful message. I mean, we have all been on the receiving end of that exact frustration.
Oh, absolutely. It is the ultimate dead end for a user. It leaves you feeling completely powerless. But today, we're going to look at that exact scenario, but we are slipping the screen around.
Yeah, we're going under the hood.
Right, to see how the software itself communicates those failures internally, before they ever reach your monitor.
And we are pulling from a really fascinating source for this deep dive. It is a highly specific, real-world programming journal entry from a developer named Ang.
Published literally today, right?
Yes, today, June 3, 2026. It's titled Notes on Haskell Programming Part 152. And it details the process of completely overhauling the error handling in a Haskell application. Ang calls it switching to strongly typed and centralized error handling.
Which I know that title sounds deeply technical.
It really does.
But what Ang is actually doing here is essentially a masterclass in architectural problem solving. Like, this isn't just about moving lines of code around for the fun of it. It is about building a precise vocabulary for failure.
And that is exactly what grabbed me. We are going to frame this not just as a coding tutorial, but really as a crucial lesson in clear communication, like how a program talks to its developer.
Yeah.
But I guess before we can appreciate the elegant solution Ang came up with, we really have to look at the messy reality of the code base prior to this overhaul.
Yeah, you kind of can't appreciate the organization until you understand the chaos.
Exactly. So Ang was building this console application called X2 eBook. And essentially, it's a tool for converting various document formats into ebooks.
Super useful tool.
Very useful. But according to the journal, the errors in this application were being handled completely inconsistently. Like, when something failed, the program would often just throw a regular string type, literally just a raw string of text saying, something went wrong.
Right, and using a plain string of text to handle an error is incredibly common, especially in, early stage development.
Really? Why is that?
Well, it is just the path of least resistance. You are a developer, maybe it is late at night, you are writing a function to open a file, and you realize, oh wait, I need to handle the case where the file doesn't actually exist.
So you just take a shortcut?
Pretty much. The quickest, easiest thing to do is just write a line of code that throws the text, file didn't open, or, conversion failed, and you tell yourself, hey, I will come back and make it more robust later.
But later never actually comes.
Exactly. Later never comes. And the problem with throwing strings is that human language is highly ambiguous to a computer.
Because it was just C's characters.
All right, right. To the machine, file didn't open is just a meaningless sequence of letters. The program can't easily parse it, categorize it, or, most importantly, trigger a specific automated recovery process based on it. It just knows some text was generated.
Okay, but Ang notes that the app wasn't entirely built on strings, right? Like, there were also some custom error types, but they were just scattered across different modules.
Yeah, it was a bit of a mixed bag.
Because Ang shares a piece of the original code representing a specific conversion error. And it grouped a few related failures together. So if a document conversion failed, this specific type could tell you if, say, the format was unsupported, like an unsupported format, export format error. Or if there was a problem with the template, it threw a template error string. Or if the underlying tool, which is something called pandoc, if that crashed, you got a pandoc runtime error, panda hacker. And finally, if there was an issue generating the final text, it was an ebook generation error text.
So that scattered approach, having a custom error type for conversions over here, and maybe another custom error type for file handling over there, and then just generic strings everywhere else, it's actually a fascinating evolutionary step in a code base.
How do you mean?
Well, the developer recognizes that strings aren't enough, right? So they start building specific categories. The conversion error Ang created is a massive step up because it attempts to answer the question of why the failure happened rather than just vaguely announcing that it happened.
I like to think of it with an analogy. Having those generic strings mixed with scattered specific array types, it feels like going to the doctor because you feel terrible, right? And the doctor just writes sick on your medical chart.
Which is technically true.
Exactly. It's technically true. Just like an error string saying failed is technically true. But it is completely useless for the pharmacist trying to figure out what medicine to give you.
Oh, for sure. The pharmacist needs a specific diagnosis to take a specific action.
Right. And even if the doctor does figure out your exact illness, if they file that detailed diagnosis away in some random cabinet in a completely different building across town, the pharmacist still can't help you.
Right, because they can't access it.
Exactly. The information exists, but the system is just too fragmented to use it effectively.
And that fragmentation introduces a really severe issue in software engineering. We call it cognitive overload.
Cognitive overload.
Yeah. Think about trying to navigate a sprawling city where every single neighborhood has entirely different traffic laws. In one neighborhood, a red light means stop. In the next, a blue triangle means yield.
That sounds like a nightmare.
It is. When a developer is working in a scattered codebase, a function might call another function, which calls a third function across totally different modules. If they all have completely different ways of reporting failure, the developer has to constantly hold that entire map in their head.
So they're constantly translating.
Yes, they have to translate between these different vocabularies on the fly.
So the developer just gets exhausted trying to figure out how to interpret the failures.
They get completely overwhelmed.
Uh,
And when developers face that level of friction, well, human nature takes over. They fall back into the trap of using plain strings for new errors because they just don't want to deal with the headache of looking up how the custom error type in Module B is structured versus the one in Module C.
it's just too much work.
Exactly. The friction of the system actually encourages bad habits.
Mm.
And that leads to this long-term chaos where failures just cannot be handled programmatically.
Wow, okay. So if the scattered approach creates that much friction, the obvious challenge is how to corral all these different laws into a single rulebook, which basically brings us to the core of Ang's journal entry.
Right, the overhaul.
Yeah. Ang writes about converting all those remaining string types and scattered modules into a strongly typed, centralized error handling system. The solution was to create a single master data type called AppError.
Basically taking all the fragmented vocabularies and forcing them into one universal language.
Exactly. And instead of just reciting the code, I kind of want to look at what this master list actually contains. Because Ang includes an exhaustive checklist of everything that can possibly go wrong in this application.
It's a very comprehensive list.
It really is. It covers missing files, so file not found file path, files that aren't text, like not text file path, invalid text encoding, which is invalid EF,
Yep.
parsing issues with parse error string, unsupported formats via unsupported format export format, template error string, underlying system crashes through panda cronopin error string, and ebook generation error text, and even open failed string.
That is a lot to pack into one place.
It is. Every single one of these is now housed under the one umbrella of AppError. And what's wild is that it doesn't just name the error. If a file is missing, the error actually attaches the exact file path. If the system couldn't read the text, it flags the specific invalid character encoding.
I love that.
Right, it carries the receipts.
Yeah, carrying the payload is what makes this so incredibly powerful. It doesn't just say a format was unsupported,
Sure.
It carries the exact format the user tried to use. Some of the errors, like the parsing failures or system open failures, they carry the specific system message associated with the crash.
Okay, wait, hold on. I am following the logic of cleaning up the strings, but this feels like it breaks a pretty fundamental rule of programming.
With one.
Well, if XS2 book keeps growing, doesn't taking every single specific error and dumping it into one giant global bucket become a massive headache? I mean, I always hear about the importance of keeping code modular and isolated.
That is a very fair point.
Right. If you have 90 or 900 possible errors, putting them all in one central file just seems counterintuitive. Doesn't that make the code base totally unwieldy?
So that pushback is exactly what many seasoned developers would argue. It feels wrong to take a localized problem like, say, a failure in the conversion module and expose it globally to the entire application.
Right, because it breaks isolation.
Exactly. But Ang addresses this friction directly in the notes. Moving these errors to a global type actually eliminated a massive amount of redundant code.
Wait, how do you eliminate code by creating a bigger master list?
Well, think about the boundaries between those modules. Under the old system, Every time you needed to pass a failure from the conversion module to the main application, you had to write a translation layer.
Oh, I see.
Yeah, you had to write code that unpacked the specific conversion error, figured out what it meant, and maybe repackaged it into a string so the main function could understand it.
That sounds tedious.
It is. But by instituting AppError as the universal language for the entire program, Ang deleted all those translation layers. The functions no longer need an interpreter. They all speak the exact same language.
Wow. So the messy middle is just gone.
Gone entirely. And the maintainability actually improves dramatically. Think about it. If you need to add a new feature to the app next year, and that feature brings a new way for the app to break, you don't have to hunt down the specific module, learn its custom error structure, and update it.
You just go to the list.
Exactly. You go to your single source of truth, the AppError type, and you just add it to the master list.
I noticed a subtle detail in Eng's notes that perfectly illustrates the simplification. In the old setup, the error for the external pandoc tool crashing carried its own deeply complex custom type.
The pandoc error type.
Yeah. But in the new centralized list, Eng flattened it out. The new pandoc runtime error just extracts the raw string message from the crash and carries that instead. Eng actively chose to sand down some of the extreme complexity to make the global type easier for the rest of the app to digest.
Which is brilliant.
Yeah.
By standardizing that payload, Ang guarantees that any part of the application can interact with a pandoc failure without needing to import and understand the entire external pandoc library's internal structure.
So it's a deliberate choice.
Yes. It is a brilliant trade-off between specificity and usability. And, Ang also explicitly mentions that this new AppError type derives two critical traits, show and EQ.
Okay, I think Eng mentioned show in the old code too. That just means the program knows how to convert the code-based error back into readable text for the developer's console log, right?
Correct. It basically ensures the error can be printed to the screen so a human can read it.
Yeah.
But the addition of eq, which stands for equality, that is the real game changer here.
Why is that?
By deriving EQ, Ang is commanding the compiler to enable direct structural comparisons between two errors.
Okay, so the program can ask an exact question. Like, it can say, is the failure I just experienced exactly equal to a file not found error for this specific document?
Precisely. And it gets a definitive yes or no from the compiler. You just cannot do that safely with strings.
Because streams change.
Exactly. A string might say, file not found today, and tomorrow another developer might tweak it to say, could not locate file. Suddenly, any logic you wrote to check for that exact phrase is broken.
And your app just crashes silently.
Yep. Strong typing, backed by that equality check, it basically makes the architecture brittle-proof.
That is fascinating. And this shift really takes us from the theory of how Ang created this master list into how it actually gets used day to day. Because centralizing the errors fundamentally changes the developer's relationship with the code.
It changes everything about how you interact with the functions.
Right. And Ang provides the specific before and after code changes made to the module interfaces to prove this, specifically highlighting a function called openEbook as the prime example.
The type signature in a language like Haskell is the absolute core of its architecture.
Yeah.
It literally tells you what goes into a function and what comes out.
So Ang breaks down the shift in this signature. Originally, the openEbook function took a file path, performed an action, and returned a type called either.
Which is a very common Haskell pattern.
Right. It was set to return either a string or a successful empty result, just a generic string on failure. But in the new system, the signature changed. It still takes the file path and returns an either type, but now it returns either the new AppError or success.
The either concept is just a beautiful piece of logic. It builds a fork in the road directly into the structure of the function itself.
Like a literal fork.
Exactly. And by convention in this programming community, the left side of the either fork is reserved for failure, and the right side is reserved for success. When Ang swapped out the left side, replacing that generic string with the highly specific AppError, the entire nature of the function changed.
This makes perfect sense. I look at this new type signature like a detailed nutritional label on a box of food at the grocery store.
Okay, I like this analogy.
Think about it. Under the new system, if I want to use the openEbook function, I can just look at the back of the box and know exactly what is inside before I consume it. I can see the exact finite list of ingredients, like every single way this function could possibly fail is documented right there on the label.
Because of AppError.
Right, whereas the old signature, the one that just returned a generic string, that was a mystery box.
It was basically like picking up a tin can with no label other than the word food, scrawled on it with a Sharpie.
Yes. You open it and maybe it's sliced peaches, maybe it's dog food. You have absolutely no idea what kind of failure you are dealing with until it literally blows up in your face.
And this gets to the ultimate benefit Eng highlights in the journal. Readability.
Readability.
Yeah. Because of that nutritional label, a developer is explicitly clear on what failures might be produced without ever having to read the underlying logic of the function itself. They don't have to scroll through hundreds of lines of code trying to hunt down where a text string might be thrown.
Which saves a massive amount of time and mental energy. The signature just acts as an automatic form of documentation.
Better than documentation, actually. It is enforceable documentation.
What do you mean enforceable?
Well, written comments go out of date the second someone changes the code, right?
Yeah.
But this type signature is guaranteed by the compiler to be accurate. If the open ebook function suddenly develops a new way to fail that isn't registered in the AppError master list, the program simply will not compile.
Oh, wow.
The system completely refuses to build until the documentation matches reality.
That is incredibly powerful. And Eng actually shares the internal mechanics of that open ebook function, showing exactly how this boundary is maintained in practice.
Right, the internal command logic.
Yeah. Inside the function, there is a helper process where getOpenCommand takes the file path and figures out the exact system command and arguments needed to open the ebook on whatever computer it is running on. It returns a string and a list of strings for the command and arguments.
Which is pretty standard system interaction.
Exactly. Then comes the core action. It is wrapped in a function called try, which basically attempts to execute that system command via call process.
And that try function is basically the gatekeeper. Reaching out to the operating system to open a file is inherently dangerous. The operating system might be busy, the file permissions might be locked, or, the application needed to open an ebook might just be missing entirely.
Any number of things could go wrong.
Exactly. And if the operating system rejects the request, it throws an unpredictable exception. The try function acts as a safety net for that. It catches that chaotic, real-world exception before it can crash the whole app.
And because of the new architecture, we know that when the try function catches that failure, it packages it neatly into the IDER framework. Yes.
It returns that failure specifically as an AppError, likely the specific open failed string error we saw in the exhaustive list earlier, complete with the system's message attached.
Exactly.
It takes the messy, unpredictable real world of system commands and sanitizes it. It wraps the chaos in a perfectly predictable, strongly typed interface.
Because inside the boundary of AppError, everything is categorized and manageable. The chaos of the outside world is simply not allowed to bleed into the internal logic of the application.
Man, we have gone incredibly deep into the weeds of Haskell-type signatures, architectural boundaries, and, the internal mechanics of a document converter.
We really have.
But the implications of Eng's journal entry stretch so far beyond this specific code base. Like whether you are a programmer writing your own tools or just someone who relies on software to get through your day, this deep dive reveals the hidden architecture of reliability.
Because quality and reliability are never accidents. They are deliberate design choices. Exactly. Good systems, whether they are built out of thousands of lines of code or just built into how we organize our daily routines, they do not solely focus on success.
Right. They don't just plan for the happy path where every light is green and everything works perfectly.
The best systems meticulously categorize, centralize, and define exactly how they might fail, because when you know exactly how you can fail, you have the power to design an exact recovery.
Eng's migration from scattered, ambiguous strings to a unified, rigorous AppError vocabulary is just a perfect illustration of taking control over the unpredictable. It forces the developer to confront failure head-on.
It replaces that vague, infuriating error pop-up we talked about at the very beginning with a specific, actionable diagnosis. It is the fundamental difference between a doctor scribbling sick and a system knowing exactly what the treatment needs to be.
It's night and day.
It really is.
Yeah.
But looking at the sheer elegance of this solution actually leaves me with a bit of a philosophical puzzle, building right off of Eng's success.
Oh, what kind of puzzle?
Well, it's a question of scale.
Ah, right. Scale changes everything.
Exactly. Eng proved definitively that centralizing errors into a single master AppError type makes a code base incredibly readable and maintainable for a solo developer. It eliminated redundancy and provided perfect clarity for a focused tool like XS2 ebook. But at what scale does this brilliant solution start to break down?
Right, because it introduces that tension between centralization and autonomy.
Imagine a massive enterprise software project. You have hundreds of developers, dozens of different teams, all working concurrently on totally different parts of a colossal application.
It's a completely different environment.
Right. At that massive scale, does forcing every single team to register their specific failures in one single global master file become a bottleneck?
I mean, you'd have constant merge conflicts.
Exactly. Does the constant merging and updating of that one file slow the enterprise to a complete crawl? It really makes you wonder if the exact architecture that saved the solo developer becomes the anchor that sinks the massive team.
That is a very real problem in large organizations.
It is such a fascinating problem to mull over the next time an app crashes on you. Don't just get frustrated by the glitch. Think about the hidden architecture underneath and the developers endlessly trying to find the perfect vocabulary to tell you exactly what went wrong.